Hi, welcome to this talk on photonics. This talk is going to be a summary of the course EP3200 Photonics offered by the Department of Electrical Engineering at IIT Madras. My name is Ayush Jamdar. My roll number is E20B018 and I am a third year undergraduate student in the Department of Electrical Engineering at IITM. EP3200 Photonics is a course offered in the July-November semester, and this is July-November 2022 semester. Now, the goal of this brief talk is going to be to introduce the audience to what photonics is, what are the basics of photonics, what are the different concepts that went into the evolution of the study of light, and what it is today. Also, before I start the discussion, let me also give out a brief outline of why we really need to understand photonics. So what's so special about light that makes it worth understanding? Well, if you look at many applications of photonics right around us today, they are medical devices, there are measurement instruments which are known to provide much higher degree of accuracy than any other classical instruments. Light has enabled us to uh, communicate with each other at light speed, and light has hence enabled much faster communication speeds. We have been developing sustainable technologies using photonic methods, and most important, and what is really coming and waiting for us in the near future, is modern physics. This is very deeply based on quantum measurements, quantum imaging, and photonic integrated circuits, deep learning, etc. We'll come back to these applications towards the end of this talk, while then we would have established a brief understanding, a quick summary of what photonics is and how it evolved. So, coming back to the talk, this is going to be the structure. I'll first introduce the basic concepts that go into understanding light. Then we go through ray optics, which later evolved into wave optics, followed by electromagnetic optics in the previous century, and quantum optics as we see it in the 22nd century. Let's start with the introduction. Photonics is defined as the science and technology of light. It involves generation, manipulation, and studying the interaction of light with matter. The study of light started with ray optics. Later, as the Venn diagram here explains, ray optics falls into wave optics. Wave optics is again engulfed by electromagnetic optics. And finally, there is quantum mechanical optics. So this means that whatever concepts of ray optics were developed, they are enough to describe wave optics, but they are not enough to describe some special phenomenon, which are again described by properties of light uh, obtained or understood using waves. So wave optics is here hence a superset of what is studied under ray optics. Let's try to understand these one by one. As I said, applications of uh, light theory involve its use in fiber optic cables. There is LEDs, there's OLEDs, there's lasers which are used in precision cutting, metal cutting, pointing, and much more. We have always used cameras which use CMOS or CCD type of sensors. We always see screen projectors, and quantum technologies like photonic ICs are expected to be soon in our markets. Let's understand ray optics first. Ray optics is something that was the first basic understanding to light. Now, it started with a phenomenon called rectilinear propagation, which literally means that light travels in straight paths. Based on this, the geometric laws, the laws of reflection and refraction, were understood. It was empirically observed that when light hits a surface, it goes back at the same angle. And hence, the first law of reflection, that is, the angle of incidence is equal to the angle of reflection, evolved. So, once this law was stated, the second thing that follows from this is the plane of incidence. That is, the incident ray, the reflected ray, and the normal in the plane of incidence, or normal at the surface of incidence, lie in the same plane. As you can see, both of these laws are explained in the figure attached. Next came the law of refraction. Most notably, we all remember what the Snell's law is. Snell's law describes the process of refraction of light when it enters a transparent or semi-transparent medium. It states that the refractive index of the incident medium n1 times sine theta 1, the incident angle theta 1, is equal to n2, the refractive index of the second medium, and sine theta 2 multiplied by n2, which is the theta 2 is the refraction angle. This means that while light travels from one medium to the other, mu into sine theta remains a constant. And the second law here again is all of these rays lying in the same plane. Now, we are familiar with the laws of reflection and refraction and how they work with reflecting surfaces like mirrors. Now, mirror is a reflecting surface with silver coating on one side, and preferably it is glass. So when we use mirrors for experimentation, we use different kinds of mirrors. The one which is being seen here is a paraboloidal mirror. As conic sections helps us to understand that light traveling along the principal axis parallel to the FP line when incident to the mirror will after reflection certainly go through the focus. This is the characteristic property of a parabola, which is exploited in various applications for mirrors that intend to send a parallel beam of light from the focus. A special type of mirror is an elliptical mirror where it follows again the characteristic properties of an ellipse, namely, number one, light incident from one focus of the ellipse, let's say P1, when goes to the border of the ellipse after reflection, if the border is made reflective, after reflection certainly goes through the second focus. That is, a light ray emitted from one focus of an ellipse after reflection at the ellipse boundary will go through the second ellipse focus. The second property is that the distance traveled by light as it goes from P1 to the border plus to P2, the sum of this distance is a constant always. We usually deal with spherical mirrors when in lab experiments or otherwise in calculations. But spherical mirrors follow the parabolic property of sending parallel rays back through the focus under a paraxial approximation. It means that the light rays have to be close to the principal axis so as to keep up with this approximation. As the light rays go away from the principal axis, this approximation starts to go invalid. This was something about ray optics that we usually understand. Apart from mirrors, we definitely work with lenses. Lenses follow refraction, and refraction has its own properties. And these properties of light bending have enabled us to create a really marvelous device which all of us use, the spectacles. There is something really interesting that we also use very often, that is fiber optic cables. Now, it is widely believed that internet today is connected wirelessly. All the computers, all the devices in the network are connected wirelessly to each other by some satellites. But that is not true. Actually, what holds the internet together are fiber optic cables. There are around 380 underwater cables that run through the oceans across continents, and they span over around 1.2 million kilometers of distance. Most notably, you might have heard of the transatlantic fiber optic cable. These cables transmit data at near light speeds, and it is really worth understanding for how these cables work. So on the picture here at the left, you can see the cable. It has two sections, two cylindrical sections, one overlapping the other. What is inside is called the core of refractive index N1, and what covers the core is called a cladding of refractive index N2, which is less than N1. Now, what happens is that light is incident on the axis of the core. Once incident, the light enters the core, and a phenomenon called total internal reflection, is observed at the interface of the core and cladding. If you look at the structure of how fiber optic cables are built, this is a typical cable which has been used practically. So the exact center is the optical fiber, which forms the core. it is surrounded by petroleum jelly, to note that. Then there comes copper or aluminum tube, which engulfs the petroleum jelly. Then followed by that, there is a polycarbonate layer. Then there is an aluminum water barrier, because these cables have to withstand huge pressures when they're at the ocean bed, which are kilometers and kilometers down below the sea level. Then comes the layer of stranded metal steel wires, followed by mylar tape, and towards the end, finally, they are covered by polyethylene. So these wires are really thick, around this size, and uh, data transmission occurs through the optical fiber, which is sitting right inside this. Understanding fiber optics from the equations of refraction that we observed so far, the Snell's law, it is in the figure, it is seen that uh, there's something called as an acceptance cone at an angle theta a. It basically means that when light is incident on the fiber optic, fiber cables axis, if as long as the light is incident at an angle less than theta a within the cone, it will be transmitted through the fiber optic cable by total internal reflection. If the angle is less than theta a, the light will travel through it, and when the ray hits the core cladding boundary, it will get reflected totally. So whereas usually it would have been refracted, but due to the condition observed here, that the critical angle condition is followed, we will observe total internal reflection, and the light will be reflected, and it will keep on traveling through the core as towards the other end. Now, if the light ray is incident at an angle greater than theta a, it won't be able to perform total internal reflection and will hence get scattered out of the core, and that will cause data loss. Conclusion: the for data to be transmitted through a fiber optic cable, the angle of incidence of the ray has to be less than theta a inside the acceptance cone. Now, optical fibers allow single or multiple modes. What this means is that in this picture, if the light beam is incident straight along the axis of the core, it will be a single mode fiber, no reflections anywhere. But what will happen in a multi-mode fiber is that if the light is incident at an angle uh, greater than zero, then in that case the light ray will undergo reflections at the boundaries, where it is possible that after reflection the modes will scatter. What this means is that some of the modes, there's going to be different angles of incidence for different rays that are being incident, and all of them will be traveling at different angles through the ray, through the tube, and hence there will be some of the rays will have to travel a larger distance than the others, and hence they will take a little more time to reach the end. This is called multimode scattering. Now, in this diagram, there is something called a V parameter, which is given by the formula 2 pi a by lambda naught, where a is the radius of the cable. Na is something called the numerical aperture, which is given by the formula square root n1 square minus n2 square, where n1 is the refractive index of the core. Now, V parameter decides whether the incident beam is going to go as a single mode or a multi-mode. So as long as V parameter, the V value is less than 2.405, it is going to be a single mode condition. Whereas if V is greater than that, there is going to be a multi-mode propagation. Now, if you know that there's a multi-mode propagation, you can also find the number of modes by using an approximated formula for M equals 4 by pi square times V square, where M is the number of modes. This was all about ray optics that we have understood so far. This was the most elementary understanding of light that we developed. After this came scientists like Huygens and a few others who discovered different properties of light which were unexplained by the ray theory. We are talking about wave optics. So, starting wave optics, the first thing that you might have heard of is the Young's double slit experiment. Thomas Young, he was the scientist who conducted this experiment using two slits, as you can see in the figure. There are two holes in the obstruction of the opaque surface, and light is incident on it from behind. And as light propagates through the holes, through the slits, an image is formed on the screen. It was observed that instead of just having two different spots or two parallel lines, a pattern of dark and bright light intensity was observed on the screen. Well, this contradicts with the understanding of ray theory, and hence we had to understand light as waves. As you can see on the picture towards the left, light has been interpreted as waves, which explains how a wave, let's say a water droplet which falls on stagnant water, creates ripples, and those ripples move out from the point of contact as concentric circles. So this is what is being seen here. Uh, the continuous paths are something called waveforms. The waveforms are defined as the loci of constant phase, and from this, if two waves of light are in same phase, if they interfere, they'll interfere constructively. This is the term used. And constructive interference, if two sine waves of amplitude a sine omega t and b sine omega t interfere, on adding they'll become a plus b sine omega t. This, although doubles the amplitude, it increases the intensity 4 times, because amplitude is proportional to intensity square root. Now, by understanding this phenomenon, a few properties of the Young's double slit experiment were understood that that can be seen here. If the slit distance is d, and if the slit and the screen distance is d, and the distance between the two slits is 2a, you'll have to use trigonometric approximations for points close and far from the axis to find whether you will see dark fringes or bright fringes, or what the path difference between the two interfering beams will be. This was about light interference, where light is treated as a wave and both the waves interfere with each other constructively. But one more point to discuss is what will happen if they are out of phase. That is, the minima of one ray coincides with the maxima of the other. So in this case, it will be a sine omega t plus negative of a sine omega t, which adds up to 0, and which this is what causes the dark fringe on this pattern. Dark fringe corresponds to a destructive interference, where the path difference between interpreting waves is lambda, or in terms of phase, it is pi. So now that we have started understanding some phenomenon using wave theory, one more interesting phenomenon that was observed was diffraction. Diffraction occurs when light travels through uh, a small aperture, which is comparable to the diameter the aperture diameter is comparable to the wavelength of incident light. In this case, as you can see in the figure here, if the aperture dimensions are dx and dy, and light of wavelength comparable to dx dy is incident on it, the fringe pattern observed on the screen is something like a vertical and a horizontal pattern with dark bright patterns throughout. This is again because of interference, but this time there are no two different sources involved. There is just one source, and the interference pattern on the screen is caused by light waves coming from one end of the, let's say if I'm talking about around the y-axis, the y-axis distance is dy. So light wave coming from one end of this particular direction of slit to the other end along the y direction, the rays coming from these two ends of the slit will interfere together on the screen and create this fringe pattern. So the horizontal discussion that we have right now, horizontally going waves, they create the horizontal pattern here in the picture, and similarly the waves along dx will create the vertical pattern. Now there's a little more mathematical perspective to it, that uh, theta x is the angle of minima or maxima you can observe there, which is roughly given by lambda by dx and lambda by dy for the angle along y. So the plot here explains the intensity variation along y. As you might expect, maximum intensity as seen at x0, y0, but intensity does not fall down exponentially from there, or maybe you could think of it as a Gaussian distribution, but it is not like that. There are peaks again for positive values of y, indicating intensity in maximas, local maximas, and local minimas as it goes towards infinity. So this is the phenomenon of diffraction. And there are a few interesting experimental setups that are based on light interference. These apparatuses are called interferometers. We'll go through a few of them quickly, how they work and what use they find for us. So the first one here is Michelson interferometer. Now, in the figure, you can see that there is a light source giving out an intensity U naught, which is going to something called a beam splitter that is kept inclined at the center. Now, what happens is the beam splitter sends, let's say we are using the 50-50 beam splitter, which means that it sends half the intensity through it and reflects half the intensity. There is no absorption. Now, if the incident beam is split into half transmission and half reflection, the half beam which goes towards the mirror, the transmitted beam goes to a mirror. After reflection, it comes back. And similarly, another beam which was reflected goes to a mirror M1 and comes back to the beam splitter. Again, when the beams come back, they'll be splitted, reflection and transmission. The beam coming back from M1 will be reflected to the source, which will remain unaffected by the wave going back, as power supply is assumed to be constant, and the beam traveling through it is, let's say, I call it U1. U1 is the beam traveling through the beam splitter towards the photodetector. The other part of the beam which went to the mirror M2 is reflected back as U2, partially when reflected from there, it goes as the beam U2 downwards to the photodetector. Now there are two different waves that we have obtained by splitting the incident beam, U1 and U2. Depending on the path difference that these two waves have traveled through, we will be able to observe maximas, that is intensity maximas and intensity minimas at the photodetector. Now, one can also understand how this worked out at the beam splitter, because every time if the intensity halves, half of it will be going through, half of it will be going where we want it to the photodetector. For example, the reflection from mirror M1, half of it went downwards, half of it went towards the right source. Similarly, half of it was reflected from the mirror M2. So this is how we get the intensity at the photodetector. This was Michelson interferometer. Let's see two more. This is a Mark-Sender interferometer where two beam splitters are used. In a Michelson, we use just one. Now here, the light source U0 goes to the first beam splitter. Again, there is reflection transmission, goes to the mirror. From the beam splitter, there is something called a beam combiner being used here. Again, the two light beams come back at the beam combiner, reflect, transmit, and we have U1 and U2 at the photodetector. Again, U1 and U2 have traveled through different paths. You can see the paths in different shades used in the picture here. Now, based on how these two interfere, based on the path difference that they have traveled through, we'll be able to analyze whether we see constructive or destructive interference at the photodetector. Let's say we shift the mirrors towards or away from the other mirror, we will be inducing a path difference which will cause the fringe pattern at the photodetector to shift from dark to bright fringes. Hence, based on the number of fringes shifted, we will be able to understand how much path difference we have induced. There is an interesting interferometer called the Sagnac interferometer, which is used in a very uh, intriguing application at the optical gyroscope. So this is like the Michelson, just that it has one more mirror, one beam splitter, three mirrors. So the light source is incident on the beam splitter, the beam splits, it reflects. So the reflected beam is going to travel through the mirror in clockwise direction, whereas the beam transmitted through it is going to travel in an anti-clockwise direction. And when both these clockwise and anti-clockwise beams come back to the beam splitter and are partially transmitted through, they're received at the photodetector, and the path difference traveled by these two is going to be observed at the photodetector. Now, one might reasonably think that it's just the same path they have been through. Whether they go clockwise or they go anti-clockwise, it doesn't really matter. They're going to travel the same path. Well, you're certainly right in thinking this if you are. And if you think that even if we shift the apparatus a little bit to, let's say, if I shift the both of the mirrors on the right side, so as to increase the path length, I'm increasing the path of both the clockwise and anti-clockwise going beams. So what have I really changed? So what might be the use of this? Well, coming back to what I started this particular discussion with, that it is used in an optical gyroscope, which is really a nice application for this, because a gyroscope is a device that measures angular velocity. So if this apparatus, let's say if I'm using an axis that is entering the screen here, if it is rotating about this axis, all the mirrors and the beam splitters will be going around. When this happens, when this happens, one of the two beams which is going clockwise, let's say, will have to travel a longer distance than the beam going anti-clockwise. So when they travel a longer or shorter distance with respect to each other, they are inducing a path difference between them. And when this path difference is created, they are no longer in phase, and we are going to observe a non-maximum intensity at the photodetector. This is the laser gyroscope. It uses a laser beam, uh, a phenomenon similar to what we saw in the Sagnac interferometer, and uh, it is getting really popular in precision machinery because it has a really low reaction time, because it is light that we are using. Then it has a high dynamic range. It has a high accuracy, no doubt. Dynamic range refers to low noises in these apparatus. uh, this was the ring laser gyroscope, but there is also something called a fiber optic gyroscope, which instead of a ring laser uses fiber optic cables arranged in a circular fashion. There is one more interesting application of wave optics which is used, that is widely popular in ophthalmic treatments. So this is called the optical coherence tomography. You might have seen this machine at your opticians. So uh, it involves imaging of the backside of the human eye retina, imaging using light beams, such that they don't affect your eye in any harmful way, but they are used to create an image of the retina, which is used to diagnose retinal diseases or disorders. Interesting applications of wave optics. There are a lot more, and I would definitely encourage the listener to go through those on the web. Now, when ray optics was successfully used to explain certain phenomenon like interference and diffraction, it was seen that this was not enough. There were still few more properties of light that were unexplained. For example, there is polarization of light. Now, polarization was observed by the Nicol prism experiment, where which we'll get to quite soon, where it was observed that light, although is a wave, it does oscillate, but it does oscillate in a particular direction. There is something specific about the direction of oscillation, so which was not explained by ray optics. And when we are talking about the direction of a quantity which has magnitude, we are talking about vectors. So there are vectors involved in the transmission of light waves, uh, which is the additional explanation that we require to explain these phenomena. It started with electromagnetic optics, and let's try to understand the basics of electromagnetic optics and how we try to understand light using these. The most important part, the laying foundation of electromagnetic optics was Maxwell's equations. Yes, and it is what you can see in here. If you are talking about free space, let's say, or a medium, Maxwell's equations are given by del dot D is rho times the free charge density. This is Gauss law, where if you remember it in the other form, del dot E is equal to rho by epsilon. Uh, Rho is the charge density. Del dot B is zero, which means that magnetic field has zero divergence. There are no sources or sinks of magnetic fields. Magnetic fields don't emerge or go into a point. Again, there is del cross E is equal to minus del V by del T, which is which is an important phenomenon in electromagnetic induction. This was Faraday's law. Then there is del cross H equals J free, the free charge current density, plus del D by del T. This might be recalled as del cross B is equal to uh, J plus del E by del T. This is Ampere's law. So all these laws, four of them together, are called Maxwell's laws. And as the slide says, God said Maxwell's laws, and then there was light. So, on solving Maxwell's equations for free space, we obtain the wave equation for an electric, uh, and a magnetic field oscillating together in phase, and this is what actually light is. Why? Because the constant in the wave equation happened to be c. So light was seen to be an electromagnetic wave. The equation written over here is the wave equation, where c is the speed of light, equals 1 by square root mu naught epsilon naught in free space. Now electric and magnetic fields oscillate in phase. Uh, there are vector identities that are used to find these directions. For example, uh, v cross e is the direction for propagation, and more vector equations are observed from here. Uh, Summary so far, that light is now an electromagnetic wave. It is a wave, yet it is still a wave, but it is a wave of electric and magnetic fields oscillating in space. Coming back to the idea of polarization, we have a light beam polarization. Basically, what is polarization first? So polarization is the property of light, which means that light beams, the electric field and the magnetic field, oscillate in a particular fashion. There is a particular pattern in which these oscillate. The arrows in this picture indicate the electric field oscillation. If the electric fields in a light beam can be uh, the components of the beam can be taken around along two mutually perpendicular directions, as in this figure, up and horizontal. If the net electric field, can be expressed in terms of its components along these two mutually perpendicular vectors, the light is said to be polarized. Now, what relation exists between the field along x and the field along y determines the type of polarization. But as long as you are able to break the electric field into these two parts, it is polarized. It was observed that when light was passed through a prism, this is the Nicol prism, when it was passed through it, it was observed that only half the intensity came through, and it was uh, just one of the two electric fields that we just discussed. So essentially, the polarizer filtered out one component from the light beam and sent out a linearly polarized light. Now, we might take a moment to understand different types of polarizations. So if the electric field along x and electric field along y are in same phase, although they might have different magnitudes, the resultant will add up to one vector, which is a linearly polarized light. If they have the same magnitude, but the phase difference between both of them is 90 degrees, this is a circular polarization. If the uh, phase difference is 90 degrees, but the magnitudes are unequal, this is elliptical polarization. And if nothing is equal, it is in general an elliptically polarized wave. This can be proved using conic sections formulas. Electromagnetic optics also deals with a few more relations important to understand. The refractive index, which we discussed so far, which is referred to as n here, is defined as c naught by c, where c naught is the speed of light in vacuum and c is the speed of light in the medium, the refractive index of which is being calculated, which is also equal to square root epsilon mu by epsilon naught mu naught, where epsilon and mu are the permittivity and permeabilities of the medium respectively. The epsilon naught and mu naught quantities stand for the values in vacuum. This can also be written as epsilon by epsilon naught for mediums, non-magnetic mediums, for which mu is equal to mu naught, which is equal to 1 plus chi. So chi here is the susceptibility, dielectric susceptibility of the medium. There is a quantity called eta, which is the electromagnetic impedance of the medium. So the impedance of the medium is defined by E naught by H naught square, which is equal to square root mu by epsilon. It can be observed that this impedance of free space is 120 pi, using the mu naught and epsilon naught values. Now, there is two kinds of polarization that we'll have to understand. The first is called perpendicular polarization, wherein uh, we are talking about this light ray incident on a media interface, media N1 and N2. Now, when it is incident on this interface, uh, if the electric field is perpendicular, the electric field is perpendicular to the plane of incidence. It is called perpendicular polarization, and it is hence also called transverse electric polarization or TE polarization. In this case, the reflected beam electric field amplitudes and the transmitted beam electric field amplitudes divided by the incident electric field amplitude is what is called the reflectance and the transmittance of this medium respectively. Now, if we define axes x and y as shown in the figure here, for TE polarization, you can look at the formulas in the box here, the first line of formulas. The relation is Rx equals something and Tx equals something. Those are the reflectance and transmittance ratios. Similarly, there is something called uh, transverse magnetic polarization or parallel polarization. You might have guessed it that electric field is this time parallel to the plane of polarization and magnetic field is perpendicular. So transverse magnetic. Now the formulas for reflectance and transmittance are again seen on the second line of the box, where Ry is eta 2 cos theta 2 minus theta 1 cos theta 1 divided by eta 2 cos theta 2 plus theta 1 cos theta 1. So these are the formulas for TM polarization. What we saw before was TE polarization. An interesting phenomenon is the Brewster angle, where the reflected light is polarized. So it means that the incident light on the medium was not polarized. It had both. It couldn't be into in two directions of oscillation, but after reflection, it was observed that the light was polarized. This happens when the angle of incidence on the medium is equal to theta b, that is tan inverse eta 2, the refractive index of the second medium, divided by eta 1. I'm using eta here, it is n, n2 by n1, the refractive index of the first medium. Now, this is something called external reflection, which the details of which again I'll not go into. So far we have analyzed how electromagnetic optics has evolved, how principles of electromagnetism, which arose from Maxwell's laws, were employed to understand the properties of polarization of light. Now, that's fine. That's really great that we have been able to understand so many properties of light with electromagnetic optics, which also explains interference, diffraction, uh, reflection, refraction. So everything that we have analyzed so far. So hence, electromagnetic optics is the biggest circle of the Venn diagram that we have seen so far. But still, electromagnetic optics has been insufficient to prove or justify some of the experiments which again came up in the 20th century. We'll quickly move on to what those were, but a sneak peek that we have been treating light as a wave so far, right from wave optics to electromagnetics, where everything has been a wave, an oscillating phenomenon. But will it be sufficient to describe everything that light really is? Let us see. Yes, I am talking about quantum optics. Now, the first thing before we go into anything else is that it started with two things. Is the first one being Planck's hypothesis, where the energy of an electromagnetic radiation is directly proportional to the frequency of radiation. Planck said that light consists of discrete packets of energy, and the term photon was coined by somebody else, but let's call it photon. So photon is the particle which is now being described to hold the energy packet, and all these photons together cause the light beam that carries energy. The energy of each of this photon is E, given by E is equal to h nu, where nu is the frequency of the light beam. Yes, we are discussing the frequency of the photon here. We'll quickly understand why. Because it feels a little unrealistic for a particle to have a frequency. And h is the Planck's constant given by 6.626 times 10 power minus 34 joule second. Now, why frequency? Well, this reminds us of a famous physicist. His name was Louis de Broglie. De Broglie's hypothesis say that everything is a wave and a particle. Everything is a wave and a particle. The formula which he gave was lambda equals h by mv, where if mv is the momentum of the particle, lambda is h by p. So anything, a particle, if it has momentum p, we can associate a wavelength lambda to the particle, which is given by h by p. And this wavelength lambda was later in quantum mechanics observed to be the wavelength of the wave function which describes the particle, and the wave function is again related to the probability of finding the particle at a position at a point in space. We need not think about quantum mechanical aspects of this and Schrodinger's equation and so on to study photons, but wherever necessary, I'll provide the essential details. So, on de Broglie's hypothesis, every wave is a particle and every particle is a wave. Uh, yes, we do associate a frequency, a wavelength, to a photon. Since this is a quantum mechanical property that we are talking about, yes, spooky things are expected. Now, since light consists of discrete particles, this is the formula I was just talking about, that photon momentum P is given by E by C. And if E is h nu, as Planck said, then h nu by C is equal to lambda, h by lambda, which the lambda is the wavelength associated with the photon probability distribution. Now, there are a few properties of photons that must be understood. We just discussed polarization using the electromagnetic theory, but now let's try to understand what polarization is using the quantum theory. So, if a photon oscillates along the x-axis as shown in the picture here, it is said to be x-polarized. And when the photon is revolving about the z-axis, it is said to be polarized circularly. In this picture, in this particular case, it is going to be right circularly polarized. So the polarizations of light, which we so far thought of as the directions or the patterns of electric field oscillation, are now the way a photon oscillates as it goes along the way. So this was the polarization property of photon. I did not go into the depths or the clear-cut physics of how this works, but I'll definitely encourage you to do so, to read up this interesting concept if you think there's great resources available. Another important concept of the property of the photon that we must understand is the angular momentum. There is two types of angular momentum. There is spin angular momentum and the orbital angular momentum. If in an analogy to the electron, we did have spin and orbital angular momentum with an electron, where spin could have two values. Similarly here, spin angular momentum of a photon can hold two values. What could it be? Clockwise and anti-clockwise. Let's just call it 1 and -1 for simplicity's sake. So the coming back to the circularly polarized field that we observed, you can see the electric field vector as it moves along the direction of propagation by the red arrows, the red vectors in this figure. That demonstrates how electric field varies along the path. So as the circular should go, it goes along as the tip of the electric vector traces a circle. The overall three-dimensional shape looks like a helix, the tip of the vector. So what happens here is that the photon, as it moves forward along the direction of propagation, it rotates about itself. It rotates about itself, and this rotation is what the spin angular momentum is, the SAM interaction. So if it is rotating in one direction, that will be clockwise circularly polarized, and the other direction it will be anti-clockwise circular. Another interesting phenomenon is the OAM interaction. OAM is orbital angular momentum. It is when the photon revolves about the axis of propagation as it goes forward. Uh, this is again a quantum mechanical property. How this happens is when the phase distribution of the light going forward, if analyzed, is constant radially, but it increases uniformly from 0 to 2 pi along the circle. So yeah, the phase distribution is spatially distributed in a circular manner, so that uh, well, on the right side of the picture, what is being shown as a helix is the wavefront. So if you recall, I say that wavefront is the loci of points on in same phase. So if they are in same phase, and if you see that the phase is radially constant, but it increases from 0 to 2 pi circularly. So this is the pattern that you will observe from the wave perspective, and from the quantum perspective it will be a photon oscillating about the axis of transmission as it goes forward. This is a helix. Now if I change the phase from 0 to 4 pi instead of 0 to 2 pi, it is going to create a double helix in the waveform, where there's going to be two waves and they're going to oscillate about each other as they go forward. So this is OAM interaction, the orbital angular momentum. Now let's try to understand the interaction of photons with matter. There are a few ways in which this interaction of the photon with matter could happen. This reminds me of, well, uh, why did they even think of quantum optics? Well, there was the photoelectric experiment performed by Sir Albert Einstein in 1905, which proved that when light is incident on a metal surface, a current runs through the closed circuit, implying that some electrons were ejected from the metal when light was incident on it. So this is why all of this quantum optic phenomenon was being thought of, and was later experimentally proven. But when we think of interaction of light with matter again from this perspective, the first possible interaction that is possible is we'll start with absorption. Now, what you are seeing in this picture is two different energy levels of the atom. Yeah, we are dealing with the atomic level now. So what happens here is the energy level 1 is the lower energy level. The electron is in that level, the disk there, and there is one more energy level 2, which is the higher energy level. So when a photon is incident on this space, the energy of the single photon h nu is absorbed by the electron, and this absorbed energy the electron uses to go from the lower energy level to the higher energy level. So there was h nu energy sent to the atom, but nothing came out. The electron just went to the higher state, so it has absorbed the incident energy. This is absorption. Now, there's something called spontaneous emission. What could possibly happen in this case is when the electron went up to the higher energy level, it could be a very unstable state, hence provoking the electron to go back to the ground state, the lower energy level. Now, if the electron goes back, there's going to be a loss of energy, and this loss of energy is observed as one photon being emitted. So this is the energy of the photon h nu being equal to the band gap of energy levels 2 minus 1. So this is the phenomenon called spontaneous emission. Spontaneous meaning on its own, so an emission meaning emission of a photon. Another interesting phenomenon is stimulated emission, where both absorption and emission happen together. There is one photon coming, it hit the atom, the electron took the energy, it went to the higher energy level. But what happened is, in this case of stimulated emission, the material exists in its state called an inversion state, where inversion means that there are more electrons in the higher energy state, but they won't drop down back to state 1, the lower energy state. So they are probably just looking for an incentive to go back to the lower energy, and this is provided by an incident photon. So what happens here is the incident photon somehow makes the electron in the higher energy level uh, go down to the lower energy, and hence the presence of one incident photon caused the emission of another photon by this drop down, and hence two photons came out as a result. So the incident photon stimulated this emission, hence it is called stimulated emission. Now, if you look at this figure closely, you will see the phenomenon in work. So two of the very popular things that we are really familiar with, fluorescence and phosphorescence. Well, phosphorescence is not a new thing. There's glow in the dark stickers which we use, or this is also called radium sometimes, uh, and these are used in wristwatch needles so as to spot them in the dark. Well, how they work is the same phenomena which we just discussed. So when light is incident on the surface of this such a substance, the electrons which are in the lower energy state S0 get excited to the state S1 and S2. Now S1 and S2 are higher energy states. What happens is electrons, when they go to the higher energy state, they may quickly uh, lose out their energy and come back to state zero by emitting photons. This phenomenon is called fluorescence. If you can see in the diagram, fluorescence corresponds to a smaller band gap compared to what the electrons went to from S0 to S2. So this is going to be a low energy and hence a higher wavelength being emitted out. So this is a very quick phenomenon. You incident light on the surface, and it will give out light at the same time, but light coming out is of a different wavelength than the light coming in. So you're likely to see a different color coming out. This is fluorescence, which takes around 10 power 9 to 10 power minus 6 seconds. The phenomenon which I started this discussion with is called phosphorescence, where something called interstate conversion takes place, where I must inform what S and T means. So T1 is another state here. S means a singlet state, and T stands for a triplet state. Now, the excited singlet state electrons undergo interstate conversion from singlet to triplet and go to the state T1. And T1 is, you can say, a stable state, wherein electrons can stay for a longer time, and the decay back to S0 from T1 is a very slow process. So it can take, as it reads there, around 1,000 seconds also. This means that there will be a slow downfall of electrons, and it means that there is going to be a continuous emission of light. So this is what is seen in the glow in the dark stickers. Interesting, isn't it? Now, we are going to this new part where it is something called a laser. So laser is actually an acronym which stands for light amplification by stimulated emission of radiation. So the picture you are seeing here is the experiment apparatus used by Dr. H.T. Maiman, who started this pioneering laser technology, wherein he used a ruby rod in a reflective cylinder, a high intensity flash lamp to create inversion, uh, and the laser beam is coming out from the other end. So this is an optical cavity where there is 100% reflective mirror on one side and a 95% reflective mirror on the other side. So every time electrons go through the gain medium is the material, semiconductor material. When they go through it, they cause stimulated emission, which we just discussed. So every time an electron goes, it brings another photon with it, and when both of them go, they bring four more with them. They go at the mirror, they reflect, they come back from the mirror, they again bring more electrons with them, and so on. This keeps on amplifying the light intensity until the intensity which is being sent out from the 95%, the 5% which is going out from the other mirror, the power going out, when this becomes equal to the input power supply, a steady state would be achieved, and this steady state laser intensity is observed. The figure on the right explains the phenomenon of avalanche uh, stimulated emission. Now, lasers use pumping. As we saw that lasers do need inversion to start. So this inversion can be created in a few ways. The first method discussed here is a three-level pumping, where the pump, the external power supply, will push the electrons from the ground state to the state 3, which is a short-lived state from which the electrons will rapidly fall to the second state, state 2, which is a long-lived state. They won't come back to state 1 unless provoked to. So there is when the laser photon hits the stage 2, uh, photons are again emitted from electrons fall down. There's one more photon that joins the party, and then all of them together create a high intensity beam. So this is three level pumping. Now, four level pumping can be easily understood that the electrons go from 0 to 3, from 3 to rapidly to 2, and 2 to 1. 2 is a long lived state, while 1 is a short lived state. So, when they fall down from 2 to 1, they don't stay at 1 for a long time and rapidly fall down to the ground state. And this generates the required photon. Now, coming back to semiconductors. So, semiconductors are materials where the band gaps are separated by uh, by an energy level just enough for us to manipulate them to act as conductors and insulators as per our wish. So, as you can see here, the electron, the EK diagrams for silicon and gallium arsenide are shown here. So the dotted figures indicate the band gaps where it is one. The band gap is 1.12 eV for silicon and 1.42 eV for gallium arsenide. The other part of the figure, which is the graph, is the variation of the band gap with k, where k is the wave vector. So yeah, band gap also depends on that. And if the minima of the upper band, that is the conduction band, is coincides with the maxima of the valence band, it is said to be a direct band gap semiconductor. Uh, so gallium arsenide here, in the second figure, is a direct band gap semiconductor, uh, based on which we'll be able to analyze a few more properties of light. We'll see how LEDs work. So LEDs work using a PN junction diode, where the diode is used under forward bias. Some of the terminologies are used in solid state devices. You may look up that. When used under forward bias, electrons go through the band gap and a photon is emitted. They cross the depletion region and the photon is emitted. This is the basic working principle of LEDs, the light emitting diodes. Photoelectric effect, coming back to Einstein's photoelectric effect. It is seen that the electrons go from the valence band, they cross the Fermi energy level, enter the conduction band, and are kicked out of that. So once they enter the vacuum energy level, the electrons are said to be out of the semiconductor. So this is, again, there's a few terminologies. Work function is given by the band, the energy gap from the valence band's top energy level to the vacuum energy level, and there is something called chi here, which is the electron affinity, which corresponds to work function W minus the band gap. Another phenomenon, photomultiplier tubes, where a photon incident on one plate in this apparatus will eject electrons from this plate, which will go on to the next plate, which is at a potential less than the first plate. So the potential gradually falls, as you can see from the resistive divider circuitry here. So the electron goes from I was talking about the electron potential. So the electron goes from the first plate to the next one, from the next plate to the other, and what motivates it to do so is the electric potential well developed, and this electric potential, which indeed after this creates an electric field, is going to take more electrons from one plate to the next, and as they go, they keep on ejecting more and more electrons. The first one was the photoelectron, but as they go, this creates an electron cascade, and many electrons are collected at the anode. The terminals between the cathode and the anode are something called diodes. So these are photomultiplier tubes. Now, finally, we go to the discussion of photodiodes, the final topic of this discussion. So, photodiode is something that detects the presence of light. So, as it happens, uh, photons fall on the depletion region of a p-n junction. More and more photoelectrons are created in this. Sorry, not photoelectrons. Electron hole pairs are generated in this depletion region. Uh, and because of the electric field present there, they are swapped to the other regions. uh, Positive charges are swapped to the from they are go along the electric field, and the negative charges opposite to the electric field, positive charges being the holes, which are not actually charged but we treat them as holes. And uh, based on this swapping, a potential is created, and this can be seen externally. So what happens here at the exactly at the depletion region is that photons are incident on the material. As you can follow the graph on the right side, part of the photons are reflected. What is left is going through the material, being transmitted, and as it is transmitted, it is being absorbed by the depletion region to create electron hole pairs. That's why the electron reflected photon flux reduces as it goes until it has crossed the semiconductor and then is transmitted directly. Now, the electron hole pairs created will be swapped by the electric field. That is understood. The alpha used here is the absorption coefficient of the material, and this is how the photons are absorbed through the material. Now, based on which we can understand two quantities. Uh, this is something called photodiode efficiency and photodiode responsivity. So efficiency is defined as the photocurrent, number of electron hole pairs generated divided by the number of photons incident. So since electrons and holes go in opposite directions, since holes contribute to the current and electrons are opposite to the direction of current, so together they are causing a current. So this current is the photocurrent that is developed in a photodiode. So the electron hole pairs divided by incident photons is called the efficiency, photodiode efficiency, and responsivity R is defined as the current, photocurrent divided by the incident power. Units are ampere per watt. Now the formula is seen here that lambda by 1.24 is used when lambda naught is in micrometers, uh, and E, H nu are the standard constants. So this is what photodiodes are all about, and very interestingly, photodiodes are used in camera pixels to understand the incident light in wavelength, the light intensity, whether the light coming in is very bright, what color it is. In this picture, this describes a single pixel of a camera. This is a CMOS color mono and color pixel layout where there are many pixels together, and there is photodiode circuitry, which the goal of the analog circuitry is to understand what wavelength it is captured and what color it has been. An interesting application, can certainly look up to that. So yes, this is all about the very fundamentals of photonics, right from ray optics to quantum optics. We understood every basic principle that involved in the study, what was involved in the study of light. But it is really curious, makes me curious to understand what the future holds for this field. So I'll just not explain what applications each of these are just by stating them the way I did in the beginning. like I just said, there is fiber optics, there is optical coils, tomography, that's using imaging, and so on. So I'll just show you a few news clippings that I took from the web. These are these are from 2022, just this year, not even very old. I'll just read out a few of these for you. So the first one is from IEEE Spectrum. It says the future of deep learning is photonic. It says photonic quantum computer claims speed up advantage. Photonic concepts are really used for photonic integrated circuits, which are becoming widely popular these days to replace the electron circuits, because photons are being it has become possible to manipulate and detect photons much easily and faster. So the algorithms of deep learning, image processing, computer vision have been proven to run much more fast and efficiently at a low power consumption on photonic chips. So this is what is being talked about there. Another thing, single laser and optical chip pair sets data transmission, something about that. So I think you can also see the dates here. The 4 days ago corresponds to somewhere around last week of November, around November 15. So there is Silicon photonics market size worth 3.59 billion by 2028 is estimated by this firm. $1 billion economy being built on silicon photonics. Photonic integrated circuit market will hit 41,000 million dollar revenue by 2030. This is another study. One more slide on this, that China's first photonic chip production line to be ready by 2023. The second quantum revolution needs reinforcements, says another article at photonics.com. MIT News says that deep learning with light is being implemented using photonic chips. IEEE Spectrum again, it says that photonic chip performs image recognition at the speed of light. Damn, mind blowing. There's another article which says photonic processor can classify millions of images faster than you can blink. Yes, the speed of light. That is what it is. Yes, so this is just a few things, and that this is not really old. This is just the 2023 year, the current year we are living through. This is something, the data that which I obtained in November 2022. Uh, so as you can expect from this, that really this is going to be a technology of the future. There's so much that photonics has got to show the world, and hence a quantum photonic revolution is in the making. We are living in the second quantum revolution, where photonic technologies are being used for quantum measurements, imaging, and much more. With this, I conclude this brief talk on the fundamentals of photonics. This was course EP3200. I am truly grateful to Professor Shivananju B N at the Department of Electrical Engineering, IIT Madras. He is the course faculty, the course instructor for photonics at IITM. I'm thankful to him for his wonderful lectures on photonics. Thankful to him for some of the references which I've used in this presentation. I've taken from him, his slides, and again grateful to him for this wonderful opportunity to describe the course in a quick 1 hour session. I'd like to thank Vox at YouTube for their inspirational videos on fiber optics, quantum technologies, and much more. And finally, I'm very, very thankful to Canva.com for letting me create this wonderful presentation and also record it in a really great way. In the end, I would like to thank you so much, my listener, for being patient and understanding this all these concepts that go into photonics, and I hope you are ready for the quantum revolution that is coming. The future is photonic. Thank you so much.